I'm going to talk about logs and specifically about logs in the context of complex numbers. But let's start by talking about sort of high school logs, the log of a real number. Remember, the basic idea is that the log is the inverse of the exponential function. That's how you define the log. In other words, these two things are true. E to the log b is just b, or reversing that, the log of e to the a is just a. Log and e are inverse to one another. And you use that fact to prove things about the logs. In particular, you usually use this one here. This is the one that leads to some proof. So let's look at the two basic facts about logs that we're going to use. The first one is that the log of 1 equals 0. Now, how do we prove that? Well, we go over here and look at the corresponding statement using the identity up top. If the log of 1 is 0, then e to the log of 1 should be equal to 1. And then you got to ask yourself, well, then what fits in this slot? What fits in this exponent slot? Well, 0 fits in that slot. E to the 0 is 1. So that's the proof that the log of 1 is 0. Now, the second thing that we want to know about logs is this identity here. The log of AB is the sum of the two logs. How do we prove that? Well, we prove it using this identity one more time. In other words, we're going to look at this and show that this is true. And how do we do that? Well, let's just look at it just for a little practice. We know using this top identity that e to the log AB is just AB, A times B. So let's use that identity, and we have all these ops saved up here. So here it is, e to the log of B equals B. So that's going to get rid of, or that's going to simplify that side, AB. Now on this side we use properties of exponents that we know. In other words, e of a sum is the product of the two items we're looking at. So that's going to give us this. And then we use the inverse relationship one more time, and so end up with inequality that we know is true. So that's the proof of this property of log. And I always used to forget how it went, so I made up a little mnemonic for myself. Log loves a product. Log loves a product. There's the product inside. I was always confused, is it a log of a plus b or the log of a times b? Well, log loves a product and it hates a sum. So that's how I remember that. All right, now that's logs for real numbers. Actually, one final thing. Let's look at the log, the graph of a log. Here's the graph of real valued log. It zips down and crosses the x-axis at 0. In other words, or at 1. The log of 1 is 0 is what we're saying there. And I used to teach high school mathematics, and I used to tell my students think of this as a log slide, like at Disney World or someplace. You're on one of those rides that shoot into the water, and the log crashes down and it hits the water right at 1. So that's the shape of the log function. Okay, so the next thing we want to talk about is the log of complex numbers. To do that, we first have to recall a few facts about the exponent of log, or exponentiation of complex numbers. Because remember, log is going to be the inverse of x, so we have to first talk about how you take the exponent of complex numbers. So let's start with e to the z, where z is a complex number. In fact, we're going to write the real and imaginary parts of z as nu and sigma. So computing the exponent of the exponentiation or exp of z means computing the putting this sum in place of z. So let me do that by just doing a drag and a drop. And now we use a property of x that we want to hold true even in the case of complex numbers. So that means the exp of the sum has to be the product. So let's do that. And again, that's something we want to be true. We haven't shown that it is true for complex numbers, but we want it to be true. So let's assume it's true and see where that leads us. So we do that. And now we look at our pieces here. Remember, nu and sigma are both real. So this thing is an exponent xe of a real number. So that's a real number. And this thing here is sort of a new item. Let's suppose we're back in, I guess it was maybe the early 1600s when they were sorting this thing out. This didn't have a definition. What does it mean to raise e to the I power? We got to make up a definition for e to the sigma I, and the definition that works is this one. We define it as e to the ia is the cosine of a plus I times the sine of a. So it's not something that we prove. That's a definition. So if we make that substitution, we get this. And look at this thing here. This thing here is a complex number. Its real part is the cosine of sigma, and its imaginary part is the sine of sigma times I. So this turns out to be a point on the unit circle. So what we've done is we've defined e to the minus sigma, or e to the I sigma, not minus sigma, e to the I sigma, to be a point on the unit circle. And in fact, the sigma represents the argument of the point on the unit circle. Okay, so again, this is a definition. We don't have to prove that this is true. We're defining this to be true. But then what you have to prove is that if it's defined like that, then the familiar properties of exp carry over to complex numbers. In particular, exp of a plus b is equal to exp of a times exp of b. And the reason this definition works here is that you get to use familiar trigonometric identities to prove things like that. We're not going to do that, but it can be done. So if we define x in that way, all the properties that are true for real numbers carry over to complex numbers. All right, now again, remember we're heading towards the idea of being able to take the log of a complex number. In order to do that, we have to talk about the polar form for a complex number. And the polar form for a complex number is this. You can write z as the product of two things. One, the modulus of z, or the absolute value of z, or the norm of z, times e to the I arg of z, where, as we've stated, e to the I arg of z is some point on the unit circle. And the arg of z is the angle that z makes with the x-axis. So let's take a look at what that means in terms of this graph up here. I click on this point here. Here's a complex number z. Here's its shadow u down on the unit circle. Clearly, z and u have the same argument. What's the argument? Well, the argument is the angle in radians from, didn't want to click there, from here out to here running along the circle, or similarly you can run along the unit circle. The angle is the same in both cases. In this case, the arg of z is 0.93. That's what we're looking at over here. That's the arg of that z. Let's look at a few more to get a feel for what the arg is. If I put z right up here where on the y-axis, then the arg of z is actually pi over 2, which is 1.57. That's this number over here. Or if I put z right over here on the negative x-axis, then the arg of z is pi, or 3.14. If I put it right here on the positive axis, what's the arg going to be? It's going to be 0. And down here it's going to be negative pi over 2. And if I approach this side but don't quite hit the y-axis, it's going to be almost negative pi. So what does that mean then in terms of z? Clearly z, the modulus of z is well, the modulus of u is 1. So we can write z as what? We can write z as the modulus of z times u. In other words, we can do this. Z is just its shadow on the unit circle expanded by whatever the modulus of z is. So in this case, the modulus is 3.58. So that means that this point here is 3.58 times bigger than the shadow on the unit circle. Or let's go back here, look at one more of these. Let's look at a simple one. Let's put our z right here on 4, or as close as we can get it to 4. There. Okay, there it is on 4, and clearly z is 4 times u. So this is true in general. We can write z as its modulus times its shadow, but remember its shadow can be written as e to the I arg of z. So in other words, we can write z as its modulus times something on the unit circle, and that something on the unit circle will always be e to the I arg z. Now that tells us how to get the log of a complex number. So how do we do that? Well, let's just let's put it in here. How do we compute the log of z when it's complex? Well, you first write z in its polar form, and inside there we see a product, and log loves a product. Log loves a product. So let's use that property of logs and break it up into a sum. And then finally we use the log and e or inverse property. So let's do that. And in fact, the log is what's known as a multi-valued function. There's more than one value that exponentiates into a given z. So I could put like a 1 where this 0 is, or a 2, and that would be a valid log too. But we're not interested in all those other logs. We just want the principal log. So let's get rid of that. So that's the principal log of z, and notice it has two parts. It has a real part here, and that is just 1.38629, and we can, we get that by going to our high school version of log, or the real valued version of log. We plug in the absolute value of z up here and see where that leads us. That leads us over here to 1.38, and that looks about right on the graph. So that's the real part of the log, and then then there's the imaginary part of the log here. If we look at that, it's going to be 0 here, and why is that? Because I chose my z out here. Let's choose some different z's. If I choose a z up here that has an arg, then it's going to be this number here. It's going to be a complex number. So let's look at a few more of those just to get the feel for it. If I take a z which is real, and we want to look at the whole thing here. If I take a z that's real, then the arg of z is 0, so of course the log comes out to be the familiar log, the real valued version of log. If I take a negative number though, then the arg of z is actually pi, and you see that down here. Here is the imaginary part of the log of z. It's pi. And of course here's the real part, and the real part you get by just going back to our familiar version of log and plugging in the modulus of z there and seeing what pops out over here. So it's about a little greater than 1, which is what we're seeing down here. Now, what about if I choose a z right on the unit circle? Let me choose I right there. That. If I choose that as my z, then what I get is purely imaginary in this case. Well, that of course is obvious since I chose I as my point. So let me choose one over here. Alright, so here's one that's close to being on the unit circle. Can't get it exactly on the unit circle, but if it were on the unit circle, absolute value of z would be 1, and so the log of the absolute value of z would be 0. So this would just take on this imaginary form here. The first part would be 0. It's not because I'm not right on the unit circle, but in general it will, if you're on the unit circle, then the log will be purely imaginary. Let's see if I can click on a few more and get that. Well, let's click on I again. I can get right on the unit circle if I click there. And there it is, purely imaginary. And if I go over here to -1 on the unit circle, purely imaginary. In fact, that's pi we see is the coefficient of I. Or down here, I can click on these points and get it to be exactly on the unit circle, and so the log is -pi/2. Let me try one not on one of these obvious points. I click on that one. Alright, again, this if I could get right on the circle, this part here would be 0, and this part here would just be the arg of z. So this part here will disappear if I'm on the unit circle, and what I'm looking at is just the arg of z, which in this case is a -0.78. So in other words, going from here to here is about 0.78 radians in the negative direction. Alright, now in the stability problems that we're going to be looking at in the next couple of modules, it'll turn out that we're only going to be interested in complex numbers. We're going to be interested in eigenvalues of a certain matrix, and those eigenvalues always end up being either on the positive line up here or on the negative line down here, or on the unit circle. In other words, we'll never see one out here, Well, in fact, we'll never see an eigenvalue in here. It's always going to be up here on the positive part of the unit circle. And in fact, well, actually, we will see some eigenvalues inside the unit circle, and turns out that they'll always be reciprocals of the eigenvalues on the outside the unit circle. So let me rephrase that then a little bit. Let's the eigenvalues that we'll be looking at will be of the form z and 1 over z, where z is out here, it's real and greater than 1, so its reciprocal will be real and less than 1. Another type of eigenvalue we'll be looking at would be a negative 1. So its reciprocal will be over here between -1 and 0. And then the third kind of eigenvalue that we're going to be looking at will be just on the unit circle. And its reciprocal will actually be its conjugate, which will be down here on the unit circle. Let me stick that in the graph so we can see that. Okay, so there it is. The red point is the reciprocal of the blue eigenvalue, and it's a conjugate. The reciprocal of something on the unit circle is in fact its conjugate. And let's look at this one more time. If I take a eigenvalue out here, its reciprocal is the red point, which is inside the unit circle. And if I take an eigenvalue out here, okay, so where was I? We were looking at the eigenvalues that we're going to encounter in the future. And well, as we said, they occur in pairs. One is the reciprocal of the other. Now let me just point something out here. We can take the log of any number we want, or the reciprocal of any number we want, but we're not going to have to deal with them. The kind of eigenvalues that pop up are just really of three sorts. There's one where it's positive and greater than 1, and so its counterpart is down here. One is going to be negative, less than -1, so its counterpart is in here. And then the other kind of eigenvalue we're going to be looking at is something on the unit circle. So we're looking at a very limited part of the full complex plane and what happens and what we see in the future. Now we're going to be talking about stability in the future. And let me, the whole idea of stability is encompassed in the following few thoughts. Let's suppose z is our eigenvalue that pops up in these future discussions. In other words, let's take a real valued z right here. What happens as you raise z to different powers, to ever higher and higher powers? Well, clearly if the modulus of z is greater than 1, this thing is going to fly off to infinity. And we can see that over here. This is getting bigger and bigger. As I make n larger and larger, it's going to get small. It's going to get larger and larger. And what happens to the reciprocal? Well, it goes to 0. So as far as stability is concerned, we would say that this one diverges to infinity, and this one converges to 0. And that's true for any point out here. If our eigenvalue is real and greater than, well, if it's real, even if it's down here, if it's real, they occur in pairs. So one's going to be down here and one's going to be up there. If that's the case, one of those eigenvalues, or these z's down here, is going to run off to infinity, and the other is going to run off to 0. That's the same for negative eigenvalues. They flip around with n. That's how the negatives are different from the positive. As n increments by 1, the modulus, or the eigenvalue, actually pops from one side, from the negative side to the positive side. So that's how they're different. And then there's the the third type of eigenvalues that we look at, that are something on the unit circle. So what happens to those as you raise n to ever higher and higher powers? Well, they stay on the unit circle. The modulus is 1, and raising z to a power means raising its modulus to a power, and 1 raised to the 50 is still 1. It also means raising its e to the I z part, or e to the I arg part, to a higher number n, but that just multiplies the arg. You zip around the unit circle. You're going to be at a different point on the unit circle, but you're still going to be on the unit circle. So if your eigenvalue is on the unit circle, you have periodicity. You don't diverge to infinity or converge to 0. And I think that's enough for this.